So let's go ahead and get started. Good morning or good afternoon, depending on what time zone you're in. Welcome to the Q-Chem webinar. We're really excited to have all of you joining us today, and we're also very excited to have Avik Ojha from The Ohio State University. And he's going to be presenting on some of his spectroscopy work that he's been doing in Q-Chem recently. So before we get started, just a little bit of an introduction to Avik. He is currently working on his PhD in theoretical and computational chemistry at The Ohio State University in Professor John Herbert's group. He got his BS from St. Xavier's College in 2019, and then in 2021, he got his master's at the Indian Association for the Cultivation of Science. After which he moved to The Ohio State University, where, as I mentioned, he's working in Professor Herbert's group on electronic structure methods, excited state theory, and X-ray absorption spectroscopy. Some of the work that he's going to be talking about today as part of his talk, and especially with an emphasis on implementing methods to model core-level spectroscopy for open shell molecules. He's contributed many useful features to Q-Chem over the last couple of years, including the CVS XCIS implementation, or XCIS-CVS implementation, which is now available in Q-Chem 6.4, along with a couple of other methods that we're really excited to have as part of our Q-Chem spectroscopy suite. So we're really grateful to the contributions that he's been making, and I'm really excited to hear about some of the exciting scientific work that's gone into making those methods happen. So anyway, so his broader interests include developing new theoretical methods and using data-driven approaches to predict electronic and spectroscopic properties of large open shell and transition metal complexes. So without any further ado, I will go ahead and hand this over to him so he can go ahead and get started. But before we get started, quick note to all of the attendees, we are going to be holding all questions to the end. So if you have a question that you're really excited to ask, if you could post that in the chat or the Q&A, either one is fine, then we will answer it at the end of the section. So, all right, thank you so much. Without any further ado, let me go ahead and hand it over.
Okay, thank you, Shannon. Thank you for inviting me. So today what I'm going to talk about, my new method, it's now implemented in Q-Chem 6.4. It's called the extended configuration interaction singles method with core-valence separation in order to study the core-level spectra of open shell molecules. Now, today, what I'm going to talk about, first, let's talk about the property I'm interested in. Just a moment. Yeah. So the property we're interested in, it's called the X-ray absorption spectroscopy, which is a powerful technique to study the local electronic structure of molecules. So you can get the insight of the molecules by using the X-ray absorption spectroscopy. Now, so let's look at this figure carefully. So when we are giving X-rays, and when you are exciting electron, let's say from the 1s orbital, and if it is going to LUMO plus 1, LUMO plus 2, so you will get the cage spectra. If it is going from 2s orbital and 2p orbital, so you'll get the LS spectra. If it is from 3s, 3p, and 3d orbitals, you'll get the MH spectra. Now here, we are dealing with open shell molecules, and those are highly significant because due to presence of the unpaired electrons that strongly influence the electronic structures. Now, due to presence of these unpaired electrons, those unpaired electron leads to strong correlation, and there are not that many methods that can give good results for open shell molecules. Now, thirdly, we are interested in transition metal complexes. As we know, these complexes play a huge role in catalysis, energy storage, and biological systems. And most of the transition metals are open shell in nature. So there are methods that can like calculate the excited states and give you excited energies of these open shell systems, but most of the methods, like those actually like giving good results, those are highly expensive. So we want new methods that can balance between the computational cost and the accuracy. Now, let's talk about the challenges with open shell systems. Now, there are some methods like the unrestricted configuration interactive singles. The DFT version of it is the unrestricted Q-Chem DFT. So these methods are actually like, I mean, you can use these methods to get excited states, excited energies for open shell molecules. But the problem is, uh, as you are using the unrestricted orbitals, so you are treating alpha beta electrons separately. So that leads spin contamination. We'll discuss it about later, what is spin contamination. And there's another thing is the restricted open shell CIS. You can use it. It's better than the unrestricted one, as it is using the restricted open shell Hartree Fock orbitals as the ground state. So your ground state is spin complete. You will not get any kind of spin contamination, but when you are getting the excited states, that excited state wave function is not complete. So from there, you'll get some kind of errors. So these methods are relatively inexpensive. It's around n to the power fourth order, where n is the system size, but these are less accurate. So yeah, talking about these existing methods, so the main problem is using unrestricted methods or the spin contamination. What is spin contamination? Let's say you have your ground state as doublet and you want your excited states to be doublet. So you will not get exactly as the doublet. You will get something like mixture of doublet plus quadret or something like that. So mixing of different spin states, so you will get inaccurate energies of those excited states. So that's a huge problem. Next thing is, some of the open shell molecules, they have some near degenerate orbitals and they need more than one determinant. So these methods like unrestricted Q-Chem, these ROCIs are single reference method, and they cannot properly like give you the picture of these open shell molecules. Thirdly, as you are using the unrestricted one, you will get incorrect excited state description. So you will, as I said, you will not get exactly as doublet or triplet or quadret in your excited state. You will get a mixture of that, and you will get some broken symmetry in your excited states. So these are the problems present in these methods, the unrestricted Q-Chem, the unrestricted TDFT methods. So there are methods like the multi-reference CI, the multi-reference CAS-PT2, these NEF-PT2. They can give you like the most accurate results, but they are highly expensive. As I said, that so my interest is in transition metal complexes, and I wanted to like calculate for more than one or two transition metals. I cannot use these kind of methods because these are highly expensive. So I need a method that can balance between these like cost and the accuracy. Okay, so let's talk about the cost. So, so this is a basic diagram of showing you the cost versus accuracy for pre-existing methods. So if you look at the left figure carefully, so the DFT methods, it cost around n to the power 3. If you're using MP2, it's n to the power 5th order. If you're using CISD, it's singles plus doubles, it's cost out n to the power 6. The couple cluster, singles and doubles and triples is actually the gold standard. So it costs as computer scaling is around n to the power 7. And if you can do the exact wave function, the exact CI, that's a full CI, it's n factorial. So using DFT, you can use 100 of atoms. Using MP2, you can just use 50 to 80 atoms. CISD, it's 10 to 40 atoms. And when you are using CCSD triples, you can use it for less than 20 atoms. And for full CI, only several atoms. So the problem is if you are using transition metals and big systems, you cannot go beyond CCSD. Obviously, you cannot do full CI. You can like do till DFT and MP2 level. Okay, so this wave function is the exact wave function. So you have the Hartree Fock, you have your Hartree Fock wave function plus the singles, the single excitations, plus you are including the doubles. So these all together, it actually gives you the CISD, the singles and doubles. So I'm showing you this thing currently because the method I'm going to talk about, the XCIS method, currently actually lies between these singles and the doubles. So let's talk about the new method, XCIS. So it's called the extended CI singles. Now, let's look at the figure carefully. So you have a Hartree Fock, open shell Hartree Fock, the ground state, and on top of that, you are doing single excitations. So these orange block is my single excitations, and this is the ROCIS determinants. On top of that, we are doing some doubles, not the full double, some subset of doubles that is only originated from these singly occupied molecular orbitals. Now, the best part is when you are including these amount of doubles, the cost will not increase. It's exactly as the cost as the ROCIS and the TDDFT. So, so if you look carefully, so this is my ground state ROHF. So this is my triplet one. So we have like two singly occupied orbitals. So when you are exciting the electron, let's say from the core orbital, like the I, so I is my core orbital. So I bar depicts the beta orbital. So it goes, the beta orbital goes to T bar. So this kind of excitations you can find it ROCIS. Now, XCIS is basically single excitations. On top of that, simultaneously, I am removing another electron from the singly occupied orbitals. So if you look carefully in these wave functions, so first of all, the I bar, that means this beta electron goes to T bar. So this I bar electron goes to T bar, that's the singly occupied orbital. And the singly occupied orbital T, that's the T electron goes to the virtual orbital A. So these kind of double excitations are there in XCIS. So the XCIS wave function is basically the ROCIS wave function plus a subset of doubles that is only originated from these singly occupied orbitals. Now, what's the reason behind including these extra set of doubles in the singles? Now, this method originally created by Morris and Hedgorden. So they found like for nitromethyl radical, so when they tried to calculate the first three excited states, they got like 3 electron, I mean, the errors are like more than 3 electron volt. And that error is actually coming due to not including these kind of doubles. So these doubles are highly important for to get correlation for these kind of open shell molecules. So that's the idea behind including these doubles on top of ROCIS. Now, the best part is, as I said earlier, so the formal cost of XCIS is exactly as like CIS and the TDDFT. So that's the best thing. Another thing is ROCIS is not spin complete. So including these doubles, XCIS is spin complete. And obviously, as I'm choosing the ROHF orbital on top of that ROCIS, and as it is spin complete, it also eliminates the spin contamination. And thirdly, the third important thing is for open shell molecules, there are some low-lying excited states, and ROCIS cannot, cannot get the proper idea of those excited states. Now, XCIS can characterize these low-lying excited states due to addition of these extra determinants. So that's the whole characteristics of the XCIS. Now, let's talk about the implementation I did. So now I converted these XCIS method as the XCIS-CVS, where CVS stands for the core valence separation. Now, the core electrons, the gap between the core electrons and the the valence electrons are almost like 100 electron volt difference. So as I'm dealing with the core electrons, you can easily neglect that contribution of the valence electrons from the core electron. So the core valence separation is actually like helps to compute the core level excitations using an active space of small number of MOs. So you don't have to uh, consider the valence electrons as when you really want to choose like the core electrons like 1s or 2s. So you can completely remove those contributions from the full Hamiltonian. So as you are removing those contributions, so the computationally it's cheap and faster. So you don't have to diagonalize the full Hamiltonian. So you can just do it for small number of active space. Now, in experimental spectra, you will get when you are getting an XCIS, you don't know from like whether it's coming from 1s or 2s or 3s or 3p. So CVS actually helps to disentangle this contribution from overlapping elemental KLMH in complex spectra. So that's the useful of core valence separation. So if you look this figure, so this is the ground state of potential molecules. So let's say I just need the 1s orbital. So you can just choose you can just take this 1s orbital as in your active space, and you can remove all the contribution from those like the valence electrons. Now, the one important thing for core level spectra of potential molecules, like you have these singly occupied molecular orbitals, right? So when you're exciting electron from 1s, so it will go to that singly occupied orbital, then it will go to the other virtuals. So when it is going to that singly occupied orbital, you will get a pre-edge features. And those are highly important for these potential systems. And if it is going to other LUMO, the LUMO plus 1, LUMO plus 2, you will get the proper KH features. So that's the important part of these potential molecules. Now, before going to the result section, I just want to introduce like how you can use it in using Q-Chem. So this is for OH radical. So for OH radical, you have the oxygen one, and you want the pre-H and KH feature of the oxygen atom. So in the molecule section, you can just put the OH radical. You just have to give the coordinates. Then in the REM section, the important thing you need is unrestricted equals to false. So that will invoke the restricted open shell calculations. And the next thing you need, XCIS equals to true. Yes, so XCIS equals to true will give you RCIS results first. Then after that, it will give you the XCIS results. The next thing for CVS, the core valence separation stuff, you need these three types of keyword. TRT type equals to 3. So it actually controls the reduced subspace. So it controls the number of like active orbitals you need and the full subspace of the virtual orbitals. For XS, you need the like as many virtuals as you can. NSOL is basically number of orbitals you need. For OH radical, I just need KH and pre-H of oxygen. So that's why oxygen. So that's why you just need only one orbital, one oxygen 1s. So that's why I put one in the one in the N-sol section. And TRN is equals to true. It actually invoke the CVS approximation. The one more important thing, you have to before this calculation, you have to figure out like from which orbital you need the excitations. So if you look carefully about on the MOs of OH, you'll find the 1s is actually like the first orbital is basically the 1s of oxygen. So in the LS section, you just have to specify that number of that orbital. So that's why I specify 1 here. So what is actually happening? So it's actually exciting electron from that one. So this oxygen 1s, and you will get some features. So if you look carefully in this figure, you'll see these features that is coming around 530 and 535 electron volt. So that's the pH features, and around 550 to other peaks. Those are my KH peaks. So that's the features of the OH radical. Uh, so in the output section, you'll find something like this. So after the SCF, it will print something like this. So your ROCIS and XCIS calculation is happening. So as I said, I just truncate only the first orbital. I just chose only the first orbital. So it will automatically print you that. So you chose only one out of the 5 occupied orbitals, and you chose all the virtuals 64 out of 64. So that's a important section to check. The next thing, you will see the ROCIS excitation energies. So you'll get these excitation energies, and after that, after the ROCIS calculation, it will print the XCIS results. If you look carefully, the experimental results for OH is around 525 electron volt, and you can see for ROCIS, it's around 535 electron volt, and for XCIS is 532 electron volt. So you can see that inclusion of those doubly substituted determinants is actually improving the results, and it's going more towards the experimental results. So now from these results, so these are my excited energies, and these are my oscillator strength. So you can easily make a script. You can do the Gaussian broadening, and after doing the Gaussian broadening, you can exactly get a spectral like this. So that's how you can use the results from the Q-Chem output. Okay. Let's talk about the results for small molecules, small radicals. So here I computed like the 4 doublet radicals: the carbon monoxide radical, the NO2 radical, the NH3 radical, and the triplet O2 radical. So for carbon monoxide, if you look these table, so for carbon monoxide, I calculated the carbon KH. For NO2, the oxygen one. Sorry, there's a typo. So for NH3, I actually compute the nitrogen edge, and you can see here in the spectra, you'll see that this is my XCIS results. These are my XCIS results, and these above are my experimental results. So you can see the computed spectra are in good agreement with the experiment. But if you look carefully for NH3, the gap between the pH features, like this one, this is the pH features, and this is the main H features. So the gap between the pH features and the main KH features in XCIS is pretty large, and this is coming due to, due to the incomplete orbital relaxation effect in single reference methods. Now, what is orbital relaxation? So when you try to excite an electron, the other electrons try to relax the orbital to form a stable configuration. And in this kind of single reference method, these orbital relaxation effect is not that good. And if you see the errors that is coming from the experiment, it's almost like 4.8 electron volts to 7 electron volts, and these errors are actually coming due to incomplete orbital relaxation in both ROCIS and XCIS methods. Okay, next, what we have for large radicals. So here we computed for 2 large radicals. Tempo is a very common radical. It has the nitrogen and oxygen atom in it. So this is the tempo radical. So here we computed the oxygen 1s spectrum and the nitrogen 1s spectrum. So you can see here the pH features are coming with XCIS. It's really exactly matching with the experiment. Also, this is the nitrogen 1s spectrum. This is also matching with the experiment. The only thing is, if you look carefully for this one, the nitrogen 1s spectrum, these pH features, their intensity is much like bigger, much greater with respect to the K-edge features. But in XCIS, we're getting something different. The pH features intensities are lower with respect to the main edge features. So what we found that these are actually these intensities are actually like we are getting this because of the lack of dynamic correlation. Now XCIS in both the cases, in every cases, we also found in for some of the small radicals, like XCIS actually underestimates these intensities due to the lack of dynamic correlations. We also computed for another radical. It's called the glutathione radical. It has a biological significance. So we calculated and try to get the spectra. So the pH features, it's coming exactly, but if you look carefully, the gap between the pH features and the main KH features in the experiment, the gap is low. But in case of these like XCIS results, the gap is pretty large. And as I said earlier, this is coming due to the incomplete orbital relaxation thing. So that's the drawback in XCIS, both ROCIS and XCIS method. Okay, so as I said that we are interested for transition metal complexes, and so let's see how XCIS is actually working for this kind of complexes. Now we have two different complexes. These are pretty common complexes, FeCl4 2-, FeCl4 1- with two different oxidation state. So our goal is to check whether XCIS can depict two different oxidation state. So if you look carefully for FeCl4 2-, we have two important peaks. Those are the 4T2 and the 4T1. So you can see this for FeCl4 2-, it's actually matching with the experiments. You can see the two sticks, and you can see it's actually matching. For FeCl4-, there's one important peak, that's the 4T2. That's coming around these spectras are actually shifted. It's shifted around like almost like 50 to 60 electron volt, and that shifting is because of that orbital relaxation. And so the computed spectra, what I'm trying to say, these spectras are in good agreement with experiment, although we have to shift a lot, but still our main goal is to get the spectral features correctly. The next thing we tried to compare with an accurate, like highly expensive method. It's called the RAS-PT2 method, so restricted active space with second order perturbation. And we try to compute the oscillator strength, I mean the intensities of this spectra, and we found for both FeCl4 2-, if you look carefully, the oscillator strength for using RAS-PT2 are slightly greater than the XCIS results. And and obviously we can say that these intensities are lower due to lack of dynamic correlation, and RAS-PT2 has that dynamic correlation in it. So that's why their intensities are mostly exactly as the experiment. Okay, so the next thing I have, so I tried with different basis sets to see whether there is any basis set effects or not. So for FeCl4 1-, I tried to compute with all the curl basis set using the def2 SVP, the double zeta, and the def2 PD using the double zeta plus polarization plus the diffuse set of orbitals, using the def2 TZVP, the triple zeta, and the def2 TZVPD. So if you look carefully, the results from def2 to def2 TZVP, the gap is almost like like 1.2 to 2 electron volt different. I mean, the gap is like 1.2 to 2 electron volt. So the main takeaway from these thing, like if you really want to compute for, let's say, more than one transition metals or two transition metals, you can easily go with these def2 SVP or def2 SVPD. Because if you try to use these def2 TCPB high class of basis function, you just have to like, so it will take a lot of time. And obviously the computation cost is much higher if you use this kind of basis sets. So the main takeaway is like for transition metals, like if you really want to do more than 2, 3 metals, you can easily go with these small basis sets. Okay, so more results for transition metal complexes. So we tried another example. It's called copper semicarbazide. So it has copper D9 systems. So D9 systems, so only one singly d orbital. So when you try to excite electron, so it will go from 1s to 3d9 orbital. So that feature is very small in experiment. So in this figure I zoomed it out. So you can see the pH feature is very small. Now XCIS can give you these features, and that features you can see this in the red box. That feature is very small. Now the main thing is when you are dealing with these kind of systems, and so as I said, you can see the gap between the main pH, the pH features and the main H features, the gap is very high in XCIS, where in experiment the gap is very low. And as I said earlier, as I mentioned a lot of times, so this is because of the orbital relaxation that is, and XCIS cannot uh, incorporate these things properly. And okay, lastly, what I have, another example, it's to see the ligand effects. So here we try to compute spectra for titanium chloride and titanium, uh, the, the cyclopentadienyl complexes. So in titanium TiCl3, it's D1 system. So when you try to excite electron, so it will go from 1s to 3d, but that selection rule is forbidden. But we are getting a spectra in titanium chloride. It's because the 3d orbitals of titanium is actually mixed with the 4p orbitals, and that's why the 3d orbital gets a 4p kind of environment, and that's why we are getting this spectra. Now, so basically this spectra is actually coming due to the mixing of the 3D and the metal 4p orbitals. Now, if you remove the chlorine ligand, and if you incorporate those cyclopentadiene ligand, you will see the intensities are much lower. This is because this cyclopentadiene enol is a very strong donor. So due to donation, they actually reduce this 3D and 4P mixing. And you can see that's why the intensities is actually getting lower. So XCS can predict this kind of ligand effects. And so this is one of the good example to show like XCS can predict this kind of ligand effects. Uh, so I just want to conclude, note that so XCIS-CVS shows consistently better accuracy compared to ROCIS and unrestricted CIS, and aligns well with the experimental values. And so yeah, so as I did it for the core-valence separation, it's computationally efficient and fast and relatively inexpensive. So it's exactly at the cost of ROCIS. So there are remaining errors that is coming due to incomplete orbital relaxation and missing dynamic correlation. Now, the future work will be, so I've already started working on that. So we can use DFT orbital, that means the Q-Chem orbitals, instead of the Hartree-Fock orbitals. So the Q-Chem orbital has the dynamic correlation in it. So using the Q-Chem orbitals, you can incorporate the dynamic correlation in it. The next thing is we're also interested in spin orbit. To get LH and MH spectra. In order to get that, you have to incorporate the spin orbit coupling in the Hamiltonian. So using that, so you'll get the LH and MH spectra. The last thing will be our broader goal is to use XCIS-CVS in like solid state systems. So goal is to like use this method in embedding code to study the solid state systems properly. So that's all. So this is something different. This is completely different. So this is a update what I have recently done. So there are some non-covalent interactions, and there are some methods like the Hartree-Fock 3C, PBS 3C. They can like calculate and study these non-covalent interactions. So these are semi-numerical methods. Now, recently, I have implemented the analytical frequencies. So now you can like optimize and like get vibrational frequencies for like large systems. So that's a new update. And if you update 6.4, you will get all these CVS XCIS code and these features in 6.4. So yeah, I just want to thank Dr. Herbert, my group, NSF for funding this project. So every code is in Q-Chem. So if you update 6.4, you can get the like the CVS XCIS and the HF3C code. And if you want to know more about my paper, so that's the UI of my paper. And I just want to thank you. Thank you for listening. If you have any question, just let me know.
All right, wonderful. Thank you. Oh, I don't know what has happened with my camera. Hang on. There we go. Okay. Thank you so much. That was a wonderful talk. And again, I know I mentioned this earlier, but I've been, following the papers and advertising them on our social media and things like that. So it's really cool to see some of the underlying work that's gone into all of that. So as I mentioned also earlier, if you have any questions, please post them in the chat. It looks like we've got a couple already. So the first one, which I think was asked somewhere around slide 13, was how you select the doubles configurations, like what criteria you use for that selection process, and how your method is exactly the same order as CIS-DFT, because you're including some of the doubles.
Okay, so the thing is in the code, it's the loop just only using, the doubles you have to when you're including the doubles, the loop just inside the loop, so you just have to select the singly occupied orbital. That's all. So you are not using the whole doubles. So you have to like give a like a statement, if statement or something like that. So where you can just only specify that this will only include the doubles that is only originated from these singly occupied orbitals. What's the second question? It's like
I think
it's a
the scaling, I think, is what they mean. So how the method is exactly the same order as CIS DFT. Yes, yeah, they've clarified it is scaling. Yes.
oh the thing is so it's the formal scaling is basically n to the power fourth. So you are choosing the occupied and virtual. So when you are calculating the A matrices, that means my those double integrals. So their cost is exact. It's the occupied times virtual times occupied times virtual. So that's actually n to the power 4. So including that amount of doubles, it's not increasing, but it's somehow increasing like 4 times, not exactly, so their formal scaling is not increasing, but still it will increase like some 4 times of the CIS. So it's 4 times into 10⁴. Not, but yes, as we are not using the CISD is 10⁶. So, so yes, so it's just 4 times into 10⁴.
Mhm.
Uh,
Okay, thank you. And it looks like there's a follow-up question. Can you re-explain the doubles selection process, maybe using the diagram in your slide? It seems like they didn't quite get it.
yes, double selection. So basically, like, so so when you're exciting electrons, let's say you're exciting electron from the core levels, like this one, okay? Now, so if you look carefully, so if you look, these the first, let's have the first one. So I bar, that means the beta electron. So you are exciting beta electrons to the singly occupied orbitals. So I bar to T bar. So T bar represents the so I bar represents from where to where it is going. So I bar to T bar. So I bar beta electrons goes to these T bar. So now you can see the electron is here, and the simultaneously you have to remove another electron from the singly occupied one. So the singly occupied, you have like T and U. So I am removing an electron from the T to the virtual ones. So you have to do it simultaneously. So that's the doubly excitations. So this set of doubly excitations you have to include in XCIS.
Mhm. So it seems like it's a subset
Yes,
of
yes, yes,
the doubles
yes,
that is specifically defined as like excitations from one spin orbital to another spin orbital, right?
yes. So
It's like spin restricted kind of, and
yeah,
it's also restricted in terms of the orbitals that you are exciting into and out of.
yeah, you're right. So if you see if you see the core orbitals, you can see that these. So let's say you have two electron. I mean, you have two electrons in the core. So you are not removing these I electrons, the ith electron. So if you are going to remove that electron, so that will give you the full doubles. So we are restricting that class of doubles. So the loop the loop we have in the code, it's basically just to take these singly occupied one and avoid these doubly occupied orbitals.
Yes, I think that makes sense. Let us know if you still, okay, perfect. It looks like that is good. So excellent. Thank you. So then we've got two additional questions. One is how will you add the spin orbit coupling? Is it via a relativistic Hamiltonian?
So the thing is, here we don't have any relativistic effect. It's for KH, it's just you have to shift it. It's a scalar relativistic shift. So here in most of the cases, like let's go to the spectra. Like
I, I think they meant in the future work section because that's
Oh
something
yeah,
I'm not doing online. Yeah.
what I'm saying, like we already like shifted this spectra. We added some scalar relativistic shift, but for to incorporate, I mean, to get LH and MH, what we need perturbation kind of stuff. So after this, you have to add the Brett-Pauli Hamiltonian. So after that, you will see that your p orbitals it will splits into two different p orbitals. So from there you can get the spectra. So
Mhm.
it's so my goal is to add that Brett-Pauli Hamiltonian after the XCIS.
Mhm.
So that will incorporate the splitting
Okay.
properly.
Okay. Thank you. Um, And then we have another question in the Q&A, which is, in your approach to EXIS, you achieve accurate core level spectra without explicitly defining a multi-configurational active space. Could you explain what features of your EXIS framework inherently capture the important static correlation in the core region and how this compensates for the lack of an explicit active space?
True. So in the very beginning, when I was talking about the challenges with OpenShell, yeah, multi-configurational thing, the multi-reference thing is important, but here our goal is to use a single reference method to remove the spin contamination properly and to get like the extra amount of correlation using the doubles. So yes, for like transition metals with like different spin or different near degenerate orbitals, you need multi-reference character. But here, our goal is to not to use any multi-reference kind of thing. Our goal is to using single reference, how we can improve our results by adding those doubles. So that was our goal.
Mhm.
And yeah, we just wanted to remove that spin contamination problem properly. So because that spin contamination will always give you like wrong results, wrong spin, like broken symmetry. So yes, so using single reference method, we are still achieving that. So that was our goal.
That makes sense. Um, I guess I have a follow-up question, which is, are there any cases, like for high spin systems, for example, where doubles aren't sufficient to recapture that static correlation?
Mm,
It's okay if you don't know the answer to this off the top
yeah,
of your
I
head. I'm
mean,
just curious.
I have to check.
I'm just
I need,
thinking of like
yeah.
ones with a lot of unpaired electrons. Would that present a problem for this, or would it might not. I'm just I haven't I worked on strongly correlated systems in my grad school work, but we approached it from a slightly different perspective. So I'm curious if this would work for those types of systems also.
The thing is, what I found, like the the doubles that is originating from these singly occupied ones, that
Hmm.
actually those doubles actually captures the like main correlation out of it, out of most of the like I
Okay.
found it for the doublets one. I haven't checked with like most of the transition metals, but our next goal is to like check for those things. But yeah, for doublets, for like small radicals, if you just use these single like the XCIS method actually can capture those correlation properly,
Mhm.
because most of the correlation are actually coming from those singly excitation from those singly occupied orbitals.
Okay. Thank you. So someone says, nice talk. Thank you. Um, and the thank you is directed at you. That wasn't me
Oh,
responding.
well, yeah.
But yes. Anyway, so does anyone else have any questions in the chat? All right. Well, if no one else has any questions, for those of you who will go home and ponder this talk and then think of a lingering question that you forgot to ask, we will have a forum post where you'll be able to ask any follow-up questions that you might think of later, or for those of you who are watching this on YouTube. And we will be posting this on YouTube within the next couple of days. So probably sometime either tomorrow or early next week. And thank you again to all of y'all for attending and listening. And thank you again to Avik for his very excellent work with all of these methods. And thank you all for attending. Hope you have a wonderful rest of your Thursday. So
Yeah. Thank you.
take care, everyone. Bye.
Bye.